Hi everyone, my name is Victor Divya, and today I'll be talking about how we can build automated visualization tools using Streamlit. By automated visualizations, I'm referring to a scenario where your user could simply upload the data and your Streamlit tool can do a few things. For example, it can understand and summarize the data. It can generate a set of visualization goals that are relevant to the data, and then it could generate visualizations for each of these goals without any input or any code written by the user. Specifically, I'll explore how we can implement this using LIDA, which is an open source Python library that's powered by large language models. So who am I? In terms of introduction, my background and interests are in computer science, human-computer interaction, and applied machine learning. In the past, I've worked as a research staff member at IBM Research, a machine learning engineer at Cloudera. And in general, I'm really passionate about teaching and contributing to open source machine learning tools. Currently, I'm a research software engineer with the Human AI Experiences group at Microsoft Research. And what we care about are scenarios where a human works in tandem with an AI model to solve a problem. Very, very similar to what I'll sort of be walking through today. Okay, so this talk is going to have 4 high-level parts. First, I'll start with an introduction. Why a visualization is important, and why do we want to automate them? Next, I'll provide a demo of a Streamlit app that implements an automated visualization workflow. And I'll try to walk through some of the code and how that uses LIDA underneath to sort of power all of that capability. In the next section, I'll cover evaluation metrics. Now, this part is really important because to build confidence in our application before we put it in front of users, we need some sort of measure that helps us think about the performance of such a system. Finally, I'll conclude with some lessons learned and limitations of this approach and then a conclusion. So, why do we want to automate visualizations and why are visualizations important? One perspective is that visualizations are valuable because they help make data accessible. Over the years, it's my opinion that the human mind has evolved such that we can look at a chart or graph and we can sort of extract sufficient information to make decisions. So compared to looking at rows and rows upon rows of data in a table, we can look at a chart and make really, really fast conclusions. For example, we might look at a line chart of sales covering thousands of products, and we can conclude really fast that we'll make the most profit in the summer. However, while visualizations are really, really important and they serve this really globally important role, today, our current tools for visualization authoring requires quite a bit of skill and effort from the user. Specifically, to create a visualization, the user must understand the data. What are the columns in the data? What are the properties of each of these columns? Next, the user must have sufficient skill to ask the right question. And so, for example, they might sort of, based on their understanding of the data, they might need to figure out what are some of the interesting, important questions that we might learn from this data. Next, they need to figure out the right sort of representation of the chart. Do I use a bar chart, a pie chart, a radar chart? And even when they select all of that, they might need to decide, do I use the data as is? Do I apply some transformations to it? Do I do an aggregate, a bin? Do I combine multiple columns? And then finally, when they do all of these, they still have to implement that visualization, either using a drag and drop tool like Power BI or Excel, or they might have to write code in, let's say, a language like Python using Matplotlib or Seaborn. What if we could create tools that automatically understood the data, so summarize the data, tools that could generate relevant goals that are grounded in the content of the data. Then finally, for each of these goals, which may come from an automated system like LIDA, or may be provided directly by the user in natural language, how can we then take all of these and generate visualizations? And then how can we do this in a manner that's reliable? It turns out that we can leverage the strong language modeling capabilities and code writing capabilities of recent generative AI models such as ChatGPT-3, Claude from Anthropic, or Palm from Google AI. And so part of all of this realization is sort of implemented in LIDA, which is a tool to first summarize data, generate goals, generate visualizations based on goals, and then once we have all of these visualizations, we can then use natural language to edit visualizations, explain the visualizations, evaluate the visualizations, recommend the visualizations, and even generate infographics. And I'll get into what some of these means in a bit more detail. Now, the astute listener might sort of think, there are several tools in the space that sort of approach this sort of data science and analytics tool, for example, Code Interpreter. And so one sort of distinct difference in how LIDA sort of approaches this task is that first, we sort of provide a Python API, which sort of enables you to sort of reuse all of the capabilities in your own Python workflows. We also provide a web API. LIDA also comes with a built-in user experience, sort of shows how you might build this sort of applications. And then there's a focus on evaluation metrics that sort of benchmark the performance of the entire library. So let's take a look at a demo that demonstrates how we might implement an automated visualization workflow using LIDA and Streamlit. So first, we start with specifying a large language model. And in this case, we will start by using the OpenAI model. In theory, LIDA supports multiple LLM providers. For example, we could use Claude from Anthropic or local Hugging Face models or PAM from Google. And on the left sidebar, we have a few parameters that are standard for interacting with large language model. Next, the entire workflow starts by selecting a data set. In this case, we will select the weather data set. The first thing that happens is that LIDA has a summarization module. And first, it sort of implements summaries using a two-stage process. In the first stage process, we iterate through all of the columns in the data set. So in this case, this data set has about 7 columns. And for each column, we compute an atomic type. So for example, location is a categorical variable. Next, we extract non-null samples from that column. We compute the number of unique values in that column. Following this initial representation, which is the first few columns we have here, we then give that to an LLM that annotates that initial representation. And so in this case, the LLM has sort of annotated each column with a semantic type, in this case, location, a date, a number, a category, and then also a description for each of these columns. You'll also notice that we have a generated description for the entire data set. And so it turns out that once we can have this sort of enriched representation of the data, then we can then append the summary to every other request we sort of ask the LLM to come up with. Next, at this point, the user has done nothing, but then right now they already have a summary, and also they have a set of generated goals. In this case, we use LIDA to generate 4 sample goals that are relevant to this data set. And on the left panel here, we can see that this is a configurable parameter. And so here we have it selected to 4. So let's see, what did the LLM come up with? So given the weather data set, sort of ask the question, what's the distribution of maximum and mean temperatures across different locations? How does precipitation vary over time? What's the relationship between speed and weather conditions, wind speed and weather conditions? And what are the most common weather conditions for different locations? One thing to note here is that as opposed to just generating a question or a hypothesis, we task the LLM to sort of solve this as a multitask generation problem. So for each goal, the LLM is required to come up with a question. For that same goal, the LLM is required to come up with a rationale, which is sort of a description of what we might learn from asking this question. And then finally, the LLM is sort of required to come up with a title of a visualization that addresses this goal. If you're familiar with LLMs and chain of thought prompting and the general approach of asking the LLM to explain its work, we sort of learned that once we ask the LLM to sort of describe a rationale, we sort of end up with much more semantically richer questions or goals. And this is done for all of the goals that are generated. So now we have a goal. We then give that to the final module in LIDA, which is a visualization module. And so here we pair a summary, we pair it with the currently selected goal, and the LLM writes code. And so it writes code that looks like this. And then we compile that code, we perform some pre-processing and some post-processing, and we sort of show a visualization to the user. And we can do that for all of the other goals that have been generated. So for example, if we look at the question, what's the relationship between the wind speed and weather conditions? The LLM generates some code. The code is compiled and we get a visualization similar to the final goal. Now, what was the most common weather condition in both locations? And so we get a bar chart out of that. And so based on this, we can see that as at this point, the user has essentially written the code and they have been able to get a set of visualizations and not just that potential interesting questions with the data. Before I switch back to the presentation, I'd like to sort of walk through how we might implement all of this in Streamlit. So for the Streamlit app, it's a single file, main.py, and I'll share a link to the code repo at the end of the presentation. First, we sort of start out with the initial step. Step one, we sort of select our LLM, provide an OpenAI key. In step two, you have enough code to sort of provide tools to enable the user select the dataset and the summarization method. And then if we scroll down to step three, here's where we actually generate a summary of the dataset. And so first thing we do is that we instantiate a LIDA object. And then we have a single line of code where we point LIDA to the dataset. We select, provide a summary method and parameters for the large language model. And we call LIDA.summarize. Next, we can also follow the same approach to generate goals. And so in this case, it's a single line of code, LIDA.goals, and get a set of goals. Then finally, once we have a goal, we can then call LIDA.summarize. And so here, we call this single line of code, and then we get visualizations. And all the rest of the code is mostly just setting up the UI, setting up ways to collect user input and ways to sort of visualize render the output of each of these functions. Okay, so that was a quick demo. How are each of these components implemented in LIDA? Overall, LIDA provides 4 high-level modules. The first is a summarizer, and I touched on this in the demo. The task of the summarizer is to essentially work with the provided dataset, sort of come up with a compact representation of the dataset. Next, we have a goal explorer. The function of the goal explorer is to sort of take on a specific persona. And so this might be the persona of a data scientist and come up with a set of goals or exploration direction that makes sense with that data. Next, we then take the summary and the goal, and then we give that to a Vis Generator. And the task here is sort of generate code that addresses that goal, compile that code, and sort of generate visualizations. In addition to that, the Vis Generator is also able to explain the code that's been generated, evaluate it, repair it, filter it, and then execute it to sort of create visualizations. And then finally, there's an optional infographic module that can take a generated visualization and then output an engaging or interesting visualization that sort of retains the structural information in the chart, but might apply styles or other graphical properties to this chart. And so I'm going to walk through each of these modules individually. First, the summarizer. Like I mentioned in the demonstration, the summarizer is implemented across 2 stages. In the first stage, we generate a rule-based summary where we iterate over each column in the dataset, and we extract heuristics such as an atomic type for the column, min and max values, and the number of unique values. In the second stage, we give this initial representation to an LLM, and the LLM may add annotations such as a description of the entire dataset and semantic types for each of the fields. So the diagram we have on the right here is an example of what the summary data structure looks like. For each of the modules in LIDA, they're implemented using prompts. And so at each point, we write prompts that sort of guide the LLM and how we should perform the task. In this case, we sort of write instructions to the LLM. So we tell it always generate the name of the dataset, always annotate a dataset description, always generate a field description, and also to annotate semantic types with some few short examples. So based on that, we can then get the output of that and sort of render that out in a Streamlit application. Next, we have the Goal Explorer module. So we explore this as a multitask generation problem where we ask the LLM to sort of generate a question, which is a hypothesis, a visualization title, and a rationale for what we might learn from that visualization. An important detail to note here is that in order to get this multitask generation, we require the LLM to sort of output data in a structured format. In this case, we require the LLM to sort of output data that's structured as JSON. So this is an example of a prompt that we sort of use to achieve that goal. So for example, we sort of ask the model to ensure that its output is always JSON with no preamble or explanation. And then we give it a few short examples of what the structure of the output should look like. Next, we have the Vis Generator module. And so the Vis Generator module takes a goal, a data summary, and primarily writes code to address this goal. Again, an important detail here is that we do not ask the LLM to generate freeform code, but instead we provide it with a code scaffold or a template, and we instruct the LLM on what parts of the template to complete. It turns out that if we sort of take this approach, we can implement pre-processing and post-processing steps, especially to correctly extract code from the LLM's response. And in general, this improves the reliability and the quality of the entire system. As an example, here's some excerpts from the prompt that we sort of use to ask the LLM to generate visualizations. For example, we sort of emphasize that the code must follow visualization best practices. It must apply the right encoding and the right aesthetics. And then we also instruct the LLM to ensure that it uses the provided code template and it doesn't modify the structured parts of the code template. The final module is an infographic, and the goal of this module is to sort of generate stylized but graphically interesting versions of a generated visualization. And so this work is sort of grounded in research from the HCI domain that shows that infographics are more aesthetically pleasing, engaging, and memorable. And so this has a lot of applications for data story generation use cases. And so, for example, we might have a scatter plot like what we see on the left, and then we can give that to the infographics module and sort of condition that on specific prompts. Like, for example, raindrops. We have the raindrops example on the top row. So we have a scatter plot now represented with raindrops graphics. On the bottom, we have the underwater seashell art style conditioning, and we get charts that look like that. Underneath, we use a stable diffusion or latent diffusion model, and we sort of use the image-to-image translation capabilities of these models to sort of go from an actual visualization, preserve its basic structure, but come up with stylized versions of the same charts. Finally, this work also explores the idea of VisOps. And so in general, because we represent visualizations as code, we can perform a list of interesting operations on this representation. So for example, we could enable natural language-based refinement where we have a visualization and the user could sort of provide natural language instructions to sort of update the chart. So for example, the user might say things like change the color to green, change the color to yellow, zoom into the chart, translate it to a different language. And because large language models have very strong code writing as well as language modeling capabilities, they're able to perform this operation on the visualization, which is text. Next, we can do things like explanations with applications in building accessible apps. We could ask the LLM of the system to come up with a physical description of the chart. Next, we could perform self-evaluation and repair, where we sort of take all of our domain expertise and visualizations and sort of provide the LLM with a set of rubrics on which to evaluate a potential visualization. And we've seen a lot of good results in this dimension. And then finally, we could use the LLM to also solve the cold start problem, where we could take the current state of the user and sort of ask the system to sort of recommend visualizations that might also be interesting given the user's current state. Okay, at this point, we sort of look through the components of the system, but how do we evaluate such a system in practice? It turns out that this can be tricky for a few reasons. So first, large language models are stochastic. And so what that means is that as we modify the parameters of the model, let's say temperature, and we make multiple requests, we might get code that's substantially different. And we might also get code that might contain errors or bugs. And so how do we deal with that? And more importantly, how do we measure that? Next, even if we're able to generate visualizations, how might we start to make sense of the quality of the visualization, given that visualizations might be a subjective task? And then finally, how do we disambiguate between memorization and learning effects? So can we distinguish if the LLM is solving the visualization task based on the parameters it sees, or it's solving it because it's seen the specific data set or problem in the past? And so currently, there are two high-level metrics that we sort of implement to address this. The first is a simple visualization error rate. And so in our current benchmark, we take a data set of about 50 data sets. And for each data set, we task the system with generating 5 goals for each data set. Next, for each of these goals, we ask the LLM to generate a visualization across 2 visualization grammars, Matplotlib and Seaborn. And then taken together, we have about over 2,000 visualizations. And then we simply compute the ratio of how many of these visualizations lead to compile errors. Note that, like in this setup, we give the LLM only a single shot, only a single chance to generate, to go through the entire process. And so in our other experiments, we see that like we can actually drive the error rate down to 0 if we give the LLM multiple chances to, for example, take in the errors that are generated and sort of self-repair. And the graph we see on the right, the graph sort of shows a simple ablation study where we look at error rates using multiple approaches to generating a data summary. On the right, if we have no data summary at all, the LLM, as expected, has very little understanding of the data, and we have a very, very high error rate. Next, if we use a simple representation of the summary, which is just a list of columns, we have about 10% error rates. And then in the middle, if you have an enriched summary, we have about 3% error rate. Another important part of this chart is that it can be very useful as we make changes. For example, we select different LLM providers, and as we make changes to our prompting structure, as well as our pre-processing and post-processing stack, we can use a metric like this to sort of explore how each of these changes are affecting performance. Next, we also explore a metric called the self-evaluated visualization quality, where we use a really, really strong model like GPT-4 to sort of score generated visualization code across six dimensions. So first, we look at code accuracy. We ask the LLM to assess how accurate the generated code is. Next, we ask the LLM to sort of evaluate how appropriate the transformations applied to the data are. Next, we look at compliance, which is a measure of how well the generated code addresses the goal that was specified. Then we look at the suitability of the visualization type, suitability of encoding, and an assessment on the aesthetics of the chart. And it turns out that very, very large language models like GPT-3.5 and GPT-4, they have learned to encode visualization best practices and are able to provide meaningful scores on each of these dimensions, as well as rationale. In the diagram we see above, we have a pie chart, and essentially we ask the LLM to sort of evaluate the code for this pie chart across each of these dimensions. And on the dimension of type, it says that it gives the low score 2 out of 5, and says that while the pie chart can show the distribution of precipitation across weather conditions, is not the most appropriate visualization type for this data. Sort of explains that a bar chart or a stacked bar chart may be more suitable. And the reason why is that it helps us better compare our values across weather conditions. While building this project, what are some high-level takeaways that are sort of useful to share? So the first is that by transforming the code generation task for generating visualization code, by transforming that from an open generation approach to a fill-in-the-middle or prompt scaffold generation, we sort of improve reliability. And so earlier I sort of mentioned how, as opposed to asking the LLM to generate code given the summary and the goal, instead we give the LLM a code scaffold and we sort of ask it to sort of fill in the content of that. So we've observed that that approach sort of improves reliability. The next lesson is to explore opportunities to sort of inject domain expertise across the entire solution stack. So in this case, when we generate a data summary, we don't ask the LLM to come up with the entire summary. Instead, we take all that we know about data and tabular data properties, we construct an initial representation of a summary, and then we give that to the LLM to sort of annotate or enrich that representation. Next, to make the system usable and practical, we sort of figure out a setup where every single call, every single stage in the entire process is a single call to an LLM. And then finally, we found that benchmarking and metrics was critical for improving the overall design of the system. So as we made changes to the system, we could use both of the metrics that was discussed earlier to sort of assess the impact of each of these changes. Finally, there are limitations of the approach sort of described here. The first approach is that there are limitations to the performance of this system on data that are poorly represented in the training data set for very large language models. So for example, if your visualization grammar is a domain-specific language with very few examples, the performance of this entire system will be limited compared to other well-established public grammars like, say, Matplotlib and Seaborn. Next, the selection of the library has impacts on the quality of the visualization. For example, we found that the ability of the system to generate high quality visualizations for Seaborn was much better than Matplotlib and, let's say, a less known library like Altair. And then finally, because we explore a code execution approach, we need to sort of run a project like this in a sandbox just to ensure that we have a safe execution environment. So this brings me to the end of the presentation. LIDA is an open source project. Please feel free to check it out. Contributions are welcome, and thank you for listening.